All right, hey guys. So what we're going to be doing today is we're going to be going over a common problem in chemical engineering, where we're going to be talking about how pressure and temperature will change as you go down in a fluid. So in our first case, let's look at water. So we have a pool of H2O here, and we go down a depth of Z meters, or Z feet, whatever unit we use. What would be the temperature and the pressure at that point? Now we know what the temperature is going to be because in fluids like water, what happens is the kinetic and thermal energy is spread throughout the entire liquid. So for example, the temperature here will be equal to the temperature there. So T is just T initial. So we don't have to worry about temperature for this problem. But pressure will change. And to see how pressure will change, we're going to go to our good old friend, our statics equation. Change in pressure related to the change in the depth is equal to the density multiplied by acceleration due to gravity, negative. So what happens here is dP dz is, let's go ahead and move dz to this side. I'm going to go ahead, actually no, I'm going to leave rho here for right now. I have negative rho g negative rho g times change in depth is equal to change in pressure. So what's going to happen now is we could easily say, oh, density is going to be the same throughout, which it will. However, one thing you need to know about density is its mass over volume. Now, mass is just number of moles multiplied by molar mass over volume. Now, notice we have pressure in here. Now, volume, if you remember from that ideal gas law equation, or natural gas law, I mean, what's going to happen is pressure right here, we're going to move it to this side so we can replace V with it. So V is going to equal nRT over P. Now plug that in, you notice the moles will cancel, the pressure will go up top, RT go to the bottom. So we got is pressure molar mass over the gas constant times temperature. So what happens when we plug this in now? We got dP, change in pressure, once again, equal to negative pressure, molar mass, acceleration due to gravity, gas constant times the temperature of the liquid multiplied by the change in depth. So you get like terms on like sides, move this over here. So the dP over P is going to be equal to negative molar mass times acceleration due to gravity times gas constant times temperature dz. Now notice molar mass constant, gravity constant, are always a constant, and temperature in this case will be a constant. So since temperature is constant, this is an isothermal process. The reason it's isothermal, temperature stays the same because liquids like water will distribute the heat energy in it to all of its molecules, giving it the same temperature at one point at the other. get our good old friend squiggly in here. dP over P equal to negative mg, over RT times the squiggly of dz. Now our good old buddy calculus comes into play, and we're going to get a definite integral from P1 to P2, the corresponding depths of Z1 to Z2. You get natural log of P2 over P1, which is equal to negative mg RT times the change in depths. So basically all this means is how far down. So once we give the equation how far down it is, we now need to sort of get this out of the natural log. To do that, we're going to take the exponential of both sides. So P2 over B1. So it's the exponential of negative mg over RT times how far down we want to go. So with that, just simple multiplication, the new pressure will equal the old pressure times the exponential of its molar mass times the acceleration due to gravity times the gas constant times temperature of the liquid and how far down we are going. And that's going to be our pressure for isothermal processes like pools of water. Okay, so now on to our second scenario. Say we have a nice guy here by the name of Bob. And he wants to climb Mount Everest. He gets up there, but he notices it is extremely cold. But he remembers doing this problem up here, our first one, where we deal with the pole. So he is confused as to why he's feeling colder. Well, that's because going up in the atmosphere is not an isothermal process, it's an adiabatic one. So like say we're down here at sea level, which is altitude 0, and the pocket of gas goes all the way up here. Notice it expands. However, the temp in here is equal to the temp out here, and the temp in here is equal to the temp out here. That's why he's feeling so cold up here. Heat is not being exchanged here. What's happening is work is being done on the surroundings. So the system is losing energy, and to account for that, the temperature is dropping. Work on surroundings. So if we wanted to find how temperature and pressure changes here, because both temperature and pressure are changing, what we're going to need to do is we're going to have to go to our good old friend U, the change in internal energy of a system, where it is equal to a small amount of heat transferred plus the work done on the system. Now keep in mind, work is being done on the surroundings, so our work is going to be done by the equation negative PdV, where P is the external pressure, but since it is adiabatic and reversible, P external will equal P internal. So no matter which one you pick, you'll have the right answer. So just to save time, I'm just going to use P. So keep in mind, adiabatic, no heat is transferred. That goes to 0, meaning our change in internal energy is equal to negative pressure times the change in volume. Now, notice we do not have any temperature in here. Now, to input temperature in here, we are going to take this du and switch it around to the specific heating capacity at a certain volume multiplied by the change in temperature. That'll get us our change in internal energy, which will be equal to negative P dV. Notice we have temperature now. So what's going to happen here is we now need temperature as a variable. And since pressure is related to temperature and volume, what's going to happen here is we're going to need to use the natural gas law and solve for P, which will just be P equal to RT over V. Now you're going to notice I omitted number of moles. This is because to save ourselves a lot of strain, we're just going to take du and we're going to treat it as the change in internal energy per mole. So for every 1 mole, this is how much the internal energy will change. So that's right. So let's get back to this equation. So specific heating capacity, yeah, that's specified volume, multiplied by the change in temperature is equal to negative RT over V dV. Now V is already satisfied with dV, but temperature needs to go on this side so it can be with dt. So what's going to happen here is CV over R. All I did from that was just move R to this side, equal to dt over T. And on this side, all we're going to have is dV over V. Now, we'll get our good old friend squiggly back in here, T1 to T2, and then the corresponding volume measurements, V1, V2. So what's going to happen here is we're going to have negative CV over R. It's going to be equal to natural log of T2 over T1. This is going to be natural log of V1 over V2. Now notice our problem, we are concerned with temperature and pressure. We don't really care about volume too much. So, since we already have temperature, what we can do is we can use volume to bring back pressure. So volume is just going to equal RT over P. Scroll down some more. I have negative CV over R, natural log of T2, T1. It's going to be equal to natural log of R T1 P1 over RT2 P2. Notice R's cancel, P2 will come up here, P1 will come down here. I flipped the numbers around. This should be 2, and this should be 1. So with that, our equation now looks like negative CV over R, natural log of T2 T1, which is going to be equal to the natural log of T2 P1 over T1 P2. So now you notice we have 2 natural logs. So let's move this to be an exponent. So that way we can get rid of the natural logs of all together. So you have T2, T1, negative CV over R. It's going to be equal to T2, T1 times P1, P2. Let's get all our temperatures on one side and all our pressures on the other. So this will become P2, P1, because we're going to move pressure to this side. And it's going to be T2, T1, CV over R plus 1. Now I'm just going to save us some time later. We're just going to make this CP over R. So what CP is just the specific heat at constant pressure. Heat at P. Then what's going to happen is CP is just CV plus R. So notice if you do this math, 1 times R is R, so you get CV plus R over R, which just becomes CP over R. Now I'm just going to make this, go ahead and do this now. But there is a specific constant in chemical engineering known as the ratio of specific heats, K. Which is just going to be CP over CV. For example, air, which should be about 1.4 if I remember correctly. So what this means is we want CP over R. And notice we already have a CP in the numerator, but we're missing an R in the denominator. So let's multiply by R over R. That'll get us RCP over RCV. Now we have our thing here, CP over R, but we have this extra R here. We have this extra CV there. So to get rid of that, we're going to multiply by the reciprocal, which is CV over R. You do it to both sides. And now comes the fun part, because now we need to get CV and R in terms of K. So CV, easy enough, is just CP over K. R is going to be a little bit more complicated because, remember, K is CP over CV. And CP is just CV plus R. So you can say CV plus R over CV is equal to K. So this will default to 1. So we're left with R over CV. So what that means is R ends up becoming CV times K minus 1. We plug this into here. Notice we have a CP divided by a CV. So that becomes K. So K over K just cancels out. So that's gone. So all we're left with is a K minus 1. So we get K over K minus 1 equal to CP over R. So our important equation of the day is going to be pressure over initial pressure is equal to temperature over initial temperature, all raised to K over K minus 1. Now, I want you guys, myself included, to keep this in mind. Because this will become extremely important when we go down to actually solve the differential equation we're going to have. So remember when we were talking about the isothermal process, where Tp, the change in pressure, was related to change in depth by negative rho g, or negative density times acceleration due to gravity. There we go. It should be a little better. Okay. Remember, we changed that because rho actually equaled Pm over RT. We have the change in pressure, or the change in depth, equal to Pmg over RT. Notice we have a temperature and a pressure in here now. This needs to go over here because obviously it's pressure. But temperature also needs to go over here because temperature is related to pressure. So what's going to happen is we're going to have T over P dP is equal to mg over r multiplied by dz. So remember back to the equation I told you to remember. We have T over T1, K over K minus 1 equal to pressure, initial pressure, to nothing, just 1. To get rid of the exponent, we're just going to raise everything to the reciprocal, which will make it T over T1 equal to P over P1 to the K minus 1 over K. So with that relationship, what we can do is we can plug it in for T. So let's go ahead and get the constants out of there. So we're going to have P over P1, K minus 1 over K. Oh, that is not what I meant to do. Okay, we're back. Okay, so what we're going to do now, let me get my pen back out, is we're going to have T1, P, P1, K minus 1 over K, all that over P, dP. And of course, we have Rmg over R dz on this side still. We'll worry about that later. But right now, let's just focus on this side. So T1 and P1 are constants, so we can take those out. We have T1 multiplied by P1 raised to the K over K minus 1. Because since it's being divided, we can just flip the exponent and it'll be multiplied. We have P to the K minus 1 over K over P dP. Notice all this will do is make this K minus 1 over K minus 1. And with that, what we're going to do is when we do the squiggly, what we're going to do now, from P1 to P2, what's going to happen is the initial temperature, initial pressure raised to the K, K minus 1. Notice B. Oh, that looks awful. Be P2 raised to the K minus 1 over K. minus P1 to the K minus 1 over K. Notice we have P1 now from this integral, and that is the same pressure as this one. Those are the same corresponding pressures. Then, of course, since we integrated, we have to take the inverse of that. So we have multiplied by K over K minus 1. Now, for the right side of the equation, this one, all we're going to be doing is just integrating dz, and since these are all constants, they don't matter. Mg over R, and it will become dz from corresponding depth 1 to corresponding depth 2, G over R, which will be, I did not mean to draw a sad face, and I lost my pen again. Gosh dang it. Mg over R times the lower depth minus the initial depth. And finally, all I have to do is just put these together and do some simple algebra. And have T1, P1 to the K, K minus 1, multiplied by P2 to the K minus 1 over K, minus P1 to the K minus 1 over K, divided by K minus 1 over K, which is the same as saying K over K minus 1, is equal to mg delta z. Remember, this is just the same thing as saying delta z, z2 minus z1, change in depth over R. I do not know why I started doing that lowercase. It should be uppercase, because it's the gas constant, not radius. Anyways, besides that, now all I gotta move all of these constants right here to this side. That way we can be left with P2 minus P1, and then finally we're going to be left with our P2. So we divide by T1. This will just be T1. So we will be left with P2 K minus 1 over K minus P1 to the K minus 1 over K, which will be equal to our P1 to the K minus 1 over K, because we're dividing, so this will flip, times this, divided, so this will flip as well, K minus 1 over K, multiplied by this, so mg delta z over R, and don't forget we brought our T1 over as well, so we have our T1 down here. So this is what our equation looks like so far. So to get P2 by itself, we need to move this over here. So we're left with P2 to K minus 1 over K, which will be equal to P1 K minus 1 over K. We're going to go ahead and take that out just to make it easier to read. 1 plus K minus 1 over K times molar mass times acceleration due to gravity times the change in depth over the gas constant times the initial temperature. And so for our final step, raise everything to the reciprocal of K minus 1 over K. So P2 will equal P1 multiplied by 1 plus K minus 1 over K, multiplied by mg delta z for RT1, all that raised to reciprocal, which will be K over K minus 1. And that's how we find pressure with the change of depth. So for example, if we have our gas bubble up here, we know the pressure here and the temp here. We would be able to find out the temperature and the pressure of gas bubble 2 down here. Oh, that looks awful. Down here at a distance of z. So delta z. Now you may be asking yourself, how will you find temperature? Really, it's just a simple algebra step. Gz over RT1. Now this expression P2 over P1 should look extremely familiar. That's because it's the same thing as up here. The T1, T over T1. Except now we have T2 on top. So that means our corresponding temperature, be T over T1 raised to K over K minus 1. Just forgot to put that there. So we have T2, T1 raised to the K over K minus 1, which will be equal to 1 plus K minus 1 over K multiplied by molecular weight times acceleration due to gravity, change in depth, gas constant, and initial temperature. All that raised to K over K minus 1. Now I'm going to do 2 steps in one. What I'm going to do, since both of these exponents are the same, ditch them. And then after we ditch them, we can multiply by T1, giving us the following equation to solve for temperature after a change in depth. And just to recap, what we did in this video is we found the pressure as a result of a change of depth in an isothermal process, like changing depth inside of a pool, like this one. And then we also found how to find the temperature and the pressure of an adiabatic process, like a bubble going up or going down from the top of the atmosphere. So with that, that's going to end the video. If you have any questions, feel free to leave them down in the comments below. And I will also be leaving the link to this notebook in the description below. So if you guys want to look at it anymore, feel free to. Thanks for watching, and I'll see you guys in the next video.